Bringing a 100-ton commercial aircraft out of the sky and onto a narrow strip of asphalt requires exact mathematics. You have to manage incredible speeds and extreme physical forces, often in terrible weather, to ensure those wheels touch down safely. This diagram shows a stabilized approach. It's a geometric blueprint locking the aircraft into strict parameters for altitude, speed, and descent rate. The golden rule: if the plane deviates from these numbers, the crew must immediately abort the landing and execute a go-around. The margin between a routine arrival and a catastrophe is measured in mere seconds and a few dozen feet. Sticking rigidly to that stabilized approach is the only true safety net the crew has. But the sky is chaotic. When extreme weather systems roll in, they can blind a flight crew, scramble their instruments, and corrupt the vital data they need to stay on that glide path. We can see exactly how this goes wrong by looking at two specific flights: American Airlines Flight 1572 and Air France Flight 358. Both of these crews were flying complex passenger jets into severe, zero-visibility thunderstorms, pushing the physical limits of their aircraft just to find the runway. The chaos of these storms triggered a breakdown of the stabilized approach. These crashes resulted from a sudden cascade of human and mechanical errors that erased the pilot's remaining safety margins. In November 1995, American Airlines Flight 1572 was navigating a violent night storm on its descent into Connecticut's Bradley International Airport. Right as the plane was making its final approach, the airport's control tower suffered a major water leak and had to be evacuated. Because of the resulting confusion, the lower-level approach controllers fed the pilots an outdated altimeter setting. Pilots rely on altimeters, instruments calibrated by local atmospheric pressure, to know exactly how high they are. But with the wrong setting of 29.15, the instruments lagged behind reality. The pilots thought they were a comfortable 76 feet higher than their actual altitude. This graph tracks the plane's descent against a critical safety threshold, the minimum descent altitude, or MDA. This is the absolute lowest altitude a crew can fly without having the runway visually in sight. But Flight 1572 was dropping at 1,000 feet per minute, twice the normal rate. And in the dark cockpit, the first officer missed the critical call-out warning the captain that they were crossing the MDA. Because of that aggressive vertical violation and the bad altimeter data, the plane fell completely out of the safe glide path. At exactly 771 feet, the aircraft clipped a ridge of trees, ingesting thick branches that completely destroyed both engines. The MD-83 was instantly turned into a 60-ton glider. Yet, through sheer skill, the captain managed to coax the failing airframe over the airport fence and onto the runway without a single fatality. Passengers walking away unharmed is a relief, but the investigation proved that Flight 1572 is a textbook example of a vertical violation. When bad data mixes with a destabilized descent rate, the altitude safety margin vanishes. 10 years later, an Air France Airbus A340 faced a different kind of extreme test while attempting to land at Toronto Pearson Airport in the middle of a massive thunderstorm. The environmental conditions were working directly against the aircraft. Air traffic control directed the heavy jet to a short runway measuring just 2,100 feet, right as heavy rain slicked the tarmac and severe crosswinds whipped across the plane's nose at 33 knots. This schematic maps out the runway and the required touchdown zone, where the wheels need to hit for a safe stop. But fighting the intense winds, the A340 floated in the air much longer than it should have, executing a horizontal violation by landing far beyond the target box. With the runway rapidly running out, a severe human error compounded the problem. Inside a chaotic cockpit, the pilots hesitated to engage the thrust reversers, the mechanisms that redirect engine power to slow the plane down. They waited a full 17 seconds to apply maximum braking force. They had already eaten up their margin of error. The A340 ran completely out of tarmac, overrunning the end of the runway at 144 kilometers per hour and plunging deep into a nearby ravine. The sheer force of the impact ruptured the aircraft and ignited a massive fire. The cabin crew executed a flawless, rapid evacuation, getting all nearly 300 people out just moments before the jet fuel exploded. Flight 358 exemplifies a fatal horizontal violation. When environmental margins drop to zero, hesitating for even a few seconds to apply braking force makes a runway overrun inevitable. By dissecting the wreckage and flight data, safety boards proved both crashes were born from a systemic breakdown of the stabilized approach discipline. The weather may have been the catalyst, but the deviation from strict safety protocols was the cause. Media reports often celebrate heroic glider landings and rapid evacuations. In reality, these survival stories represent a total failure of the aviation safety system before the wheels ever touch the ground. At the critical moment of final approach, there is absolutely zero tolerance for error. True aviation safety doesn't rely on a pilot's ability to fight their way out of a disaster. It relies entirely on the discipline and the judgment to abort the landing before the rules are broken.